तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yesterday I mentioned that exponential divergences of phase trajectories can be characterized by a Lyapunov exponent, and a question was asked as to why I needed to take the long time limit of the Lyapunov exponent. My answer was not quite satisfactory. You can find finite time Lyapunov exponents, but it is not very relevant for the purposes we have in mind. The reason you need a very long time average is the following. If a system is chaotic, and let us look at the kind of maps we have been talking about here, then what happens is you start with a variable x0, after one time step it goes to a value x1, and then after n time steps it goes to xn and so on and so forth. If there is exponential divergence of neighboring trajectories, then the rough idea is that any initial error in x0 is amplified exponentially, and therefore xn after some time could be nonsense. For instance, if you write two numbers in binary and they differ from each other in the 100th decimal place, and at each step let us say the error doubles, then the Lyapunov exponent is log 2, because the error becomes 2 to the n after n steps, which you can write as e to the n log 2, and the lambda is log 2 in that case, which is positive. Now what will happen is that, as we will see today with a simple model, after 100 iterations the error has transmitted itself to the first decimal place, and then of course it becomes meaningless completely. So the whole idea is that xn is not computable. On the other hand, I might have a physical variable, x might represent a physical quantity, and there may be some function of x, say phi of x, which I would like to calculate, whose average value I would like to calculate on the average. As the dynamics runs, I would like to find phi of x at each instant of time, calculate the arithmetic average of all these things, and that would be the average of phi of x. So what would this be? This would be equal to 1 over n summation j equal to 1 to n or n minus 1 phi of xj, j equal to 0 to n minus 1. This would be the average value, the time average. N is time now in discrete steps of some time step, and of course if xj is not computable in this sense, then this quantity is meaningless, but I would like to know what it does over a long period of time. In principle I would like to know what this quantity is. This is the long time average of a dynamical variable or a function of a dynamical variable, and the difficulty is, what do you do if xn is meaningless, has got so much error in it that it is completely not even computable, it does not even make sense. So what one would like to do in that at that stage is to replace a time average by an average over a probability distribution called an ensemble average, and this is the whole idea of statistical mechanics, which we are going to come to very shortly. So I would like to replace this, instead of this quantity I would like to replace it by an integral over all possible values of x, some probability density of x multiplied by phi of x, and the question is, are these two equal? Is this equal to that? And the statement is, if the system is ergodic, ergodicity implies that time averages are equal to ensemble averages. In other words, you can get rid of this quantity provided you have knowledge of this probability density, and then you can convert a long time average into an ensemble average or a statistical average. For this you must be sure that this rho of x is an invariant density. In other words, it does not change under evolution itself, and to attain this invariant density the dynamics has to run for a long time, and that is why we need here to find out what this n tending to infinity limit is. We need the long time average of quantities. So this is the reason why I am interested in defining a Lyapunov exponent which is in fact an infinite time limit. First there is an epsilon going to 0 limit, and then there is a t going to infinity limit. We will see this with the help of the example we started off yesterday with. Now yesterday we looked at simple maps, one dimensional maps. In particular we looked at linear maps, and then we discovered that if you have a fixed point at the origin, depending on the slope of this fixed point at the fixed point of the map, you could either have a stable fixed point or an unstable fixed point. Now let us look at what happens if you have a non-linear map, and a non-linear map can be extremely complicated. The simplest of these models is the so called Bernoulli map. It is also called the Bernoulli shift. I will use these terms kind of interchangeably. There are very precise mathematical definitions of these terms, and the whole of dynamical systems theory in mathematics is sometimes goes under the name of ergodic theory, because you are talking about transformations of variables, and these transformations are supposed to display certain ergodicity properties. Now let me define what the Bernoulli map is. It is a map of the unit interval to itself. So you start with a number x naught between 0 and 1, and you give me I give you a rule by which you find a number x1 which is a function of x naught which also lies between 0 and 1, and the rule is the following: xn plus 1 equal to xn 2xn modulo 1. When I say modulo 1 I mean it is a fraction, and then x naught of course you start off in the interval 0 to 1. This is my map function. Now let us plot what this map function is. So the map actually says you take x to f of x, and f of x is 2x modulo 1. Now what does that function look like? So here is 0, here is 1. If this is xn and I plot xn plus 1, which is a function of x sub n, by this rule it says simply double, take the number between 0 and 1 and double it, and if you do that of course you realize this is 1. By the time you hit the point a half, the graph goes out of scale, but then you are supposed to subtract the 1 because it is modulo 1 and bring it back. That is equivalent to taking this straight line, cutting off the second piece and bringing it back here and attaching it to this, and this is a half. That is the map. This is the rule. It is a very simple rule. You can do this on the pocket calculator. Take a number between 0 and 1, double it. If it remains within 0 to 1 you leave it. If it is more than 1 then you subtract 1 and you get the fraction back, and you keep doing this. Now what are the fixed points of this map? Well, the fixed points would arise whenever the map is equal to the function x itself, whenever f of x is equal to x. So where are the fixed points? 0 is a fixed point and 1 is a fixed point. It is clear, wherever the 45-degree line intersects the map function, these are the fixed points. What is the slope of this map at the fixed points? Yeah?
How will 1 be mapped to 1? 1 will be mapped to 0.
Pardon me, 1 is equal to 0, they are equivalent points. So the moment you come to 1 it is equivalent to this immediately, yeah, right. 1 is the same as 0, 1 is identified with 0. What is the slope at these fixed points? Pardon me? The slope is 2, right? The slope at this point is 2x, the slope is 2. Is that greater than 1? Yes indeed. So are these stable fixed points or unstable? Unstable, badly unstable, right. Now the thing that could happen is if the fixed point becomes unstable, then you should ask also, is there an iterate of this map which has a fixed point? In other words, the second iterate of this map f of x might have a fixed point, and that would mean a period 2 point for the original map, because you see a fixed point means the following: in the map f of x, a fixed point satisfies x star equal to f of x star. That is what a fixed point does. But it is also conceivable that you might have the following situation. You might have f of a equal to b and f of b equal to a. This could happen, right. So you start with the number a and you do the map, it goes to a number b, and you do the map again, it comes back to a. This is obviously a period 2 cycle. It is going to flip back between a and b, keeps going, right. Now it could happen that this map has a period 2 cycle which is stable, in which case everything will fall into that. Now what is the period 2, what does the first iterate of this map look like? I have to do this map twice. So here is x and here is f2 of x. By superscript 2 I mean f of x, and f2 of x is obviously equal to 4x modulo 1, because you already have a 2x and then you have to take each of those x's and make it a 2x, so it is 4x, but everything is modulo 1. And what does that function look like? It is going to have a lot of strips, right. It is going to have a strip at a half, it is going to have a strip at 3/4 and 1/4, so it is going to be slope 4. And where are the fixed points of this map? Well, all these lines, this is a fixed point, that is a fixed point, these were the original fixed points, but now you got 2 more fixed points, these 2 points. Are they stable or unstable? Everything is unstable because the slope is now 4, which is bigger than 1, so it is even more unstable. 1 is the same as 0, it is equivalent to 0. Pardon me? If you put x equal to 1 here, you get 2 modulo 1, which is 1, right. Yeah. There are no stable points at all. If stable points exist, then you would expect they would alternate in the naive sense that we had earlier, that maxima and minima would follow each other. But this map, as you can see, the fixed points are unstable, the period 2 points are unstable also. So it looks like there are no stable points at all. What about period 3? What is the next step? f3 of x, that is going to have slope 8, and all those points are unstable as well. So you can see here what is happening is that this is 0. What is this point, by the way? 1/3, it is 1/3, this point is 1/3, this point is 2/3, and that is 1. So I start with 0, I remain at 0, I start at 1, I remain at 1, but I start with 1/3, I double it, it becomes 2/3, I double that, it becomes 4/3, but then I am supposed to subtract 1, so it comes back to 1/3 and 2/3 and so on. So it goes click clock between these two, and it is unstable. There are more. Give me an example of the next period, period 4, what will be the next thing? 1/5. I start with 1/5, it goes to 2/5, it goes to 4/5, that goes to 8/5, which is the same as 3/5, and that goes to 6/5, which is the same as 1/5, and so it clicks back. And so it is clear that you have an infinite number of unstable periodic orbits as well, an infinite number of them, but they are all unstable completely. What do you think is a set of periodic orbits? They are all unstable. It is clear that if you took any rational number, it is going to end up as part of a periodic orbit. The right way to look at this problem is actually, instead of messing around with this x here, to write these numbers in binary. So you can write any number between 0 and 1 in binary, then what happens? So let us do that, and then you will understand why it is called the Bernoulli shift. So I start with x0, and this is equal to 0 point if it is a number between 0 and 1, I could write this number as A0, A1, A2, A3 dot dot dot, a long decimal place like this, where each of the AI's is either a 0 or a 1, right. And what is x1? What is x1 equal to? Yeah, what happens here is that this stands for x0 is numerically equal to A0 divided by 2 to the power 1 plus A1 divided by 2 squared. That is what this binary decimal, if you like, stands for, right. Now I multiply by 2, then all that happens is everything shifts, and then this is equal to A0 dot A1, A2, A3 dot dot. But then if A0 is 0, there is no problem, this means x0 was less than a half, but if A0 is 1, then the number is between half and 1 to start with, and when I double it, it becomes bigger than 1, and this A0 is a 1, and that is thrown out, so it is again 0 point whatever. Now you see what is happening here, each time you are simply shifting the decimal point and throwing away the integer part. Are you losing information? Yes indeed. So is this map invertible? No, because if you give me an x1, I cannot tell you what the x0 was uniquely. Another way of seeing it is right here. If you give me an x1 or xn plus 1, there are two possible xn's from which it arose, and you can't tell which one it was because that got thrown away out there. So in this map there is loss of information in the forward direction. You can see that you can't invert the map, and the reason you can't invert the map is because the map function is non-linear. Had it been linear, you could invert the whole thing, and it is this non-linearity that is going to lead to chaos, going to lead to the problems that we have now. But we also see that every number that is rational is in fact part of a periodic orbit. What is a rational number? How do I represent a rational number here? Either it terminates after some time and then you get only zeros, or it repeats and there is a pattern which repeats, and every number for which the pattern repeats is going to become part of a periodic orbit, but we are guaranteed that the periodic orbits are all unstable completely. For instance, 1/5, for instance 1/3, what is that in this binary thing? What is that? Well, it is certainly less than a half, so there is a 0 here, it is greater than a quarter, so there is a 1 here, and then the difference between the two is 1/12, right, and that is less than 1/8, so there is a 0 here, it is greater than 1/16, so there is a 1 here, and so on. So it is, and lo and behold, you see that x1 equal to 0.101010, and this forms a period 2 cycle. And they flip flop between each other. I leave you to figure out what is 1/5. It is again a part of a period 3 cycle, and therefore you see that every rational number is part of a periodic orbit, and it is unstable. So what is evidently happening is that because it is unstable, here 0 to 1, every rational number including a rational number here for example is unstable, and it acts like a separatrix, so it throws out numbers on either side of it. But the rationals are dense on the unit interval, arbitrarily close to every point you can find a rational, and it is unstable. So in this magical system you have a dense set of unstable orbits buried in this unit interval, but most numbers are not rational. The set of rationals is a set of measure 0. You close your eyes and put a pencil on this point on the unit interval, the probability that you are going to hit a rational number is actually 0. You are going to definitely hit an irrational number for which the decimal expansion does not terminate, goes on forever, and this is unstable, it is chaotic, it is going to behave in a completely random fashion. So what happens as time goes on, and we will explicitly see this, is that the iterates of every rational number, rational initial condition, are on a periodic orbit which is unstable, but the moment you have an initial condition which is irrational, this does not settle down anywhere, it moves, it wanders all over the unit interval, and its iterates finally densely fill up the entire unit interval. So and we will prove this, we will show that there is a uniform density of the iterates of any irrational number, no matter where you start. And is this system ergodic? It certainly is ergodic. Is it conservative or dissipative? That is a much trickier question to answer, because you must know what is meant by dissipative in this problem. We do not know that yet. We will see that it is a dissipative system. This is actually dissipative, but we will see why. It is a little tricky, but we will see why. But before I do that, let us define the Lyapunov exponent for this. What do you think is the Lyapunov exponent for this problem? First of all, it is clearly chaotic. I mean, it must have a positive Lyapunov exponent. What do you think it is? It is log 2. It is easy to see, because you have the power 2 here. So I start with any x naught, I start with an x naught plus epsilon, the two of them would get separated by precisely log 2, e to the power log 2, n log 2 is how the error would propagate. We will prove that in a minute. So let us write down the formula for the Lyapunov exponent for a one-dimensional map. I defined a lambda which is a function of the initial value x naught as equal to limit n tending to infinity, limit epsilon goes to 0 in this fashion, of 1 over n log x modulus xn minus x naught, xn minus this is how I defined it. But then you could also write this as equal to limit n tends to infinity, limit epsilon goes to 0 log f n of x naught plus epsilon minus f n. Let me write this just so that you don't get confused. Y n minus x n because I start with y naught, I iterate n times, that is f superscript n of y naught, and similarly for x naught, but y naught is x naught plus epsilon. So it is equal to the log of the nth power of this guy here. But what is this equal to? And I have to take the limit epsilon goes to 0. It's, pardon me? There's a 1 over n, very important. There's a 1 over n. So this is equal to limit n tends to infinity 1 over n log d f n over dx at x equal to x naught. It is the nth derivative of this function f superscript n with respect to x at the point x equal to x naught, and the modulus of this. But you see, you could also write this as equal to limit n tends to infinity 1 over n log df xn df xn over d fx n minus 1 over dx n minus 1 df x n minus 1 over dx n minus 2 all the way up to df x1 over dx1 df modulus of this. All you have to use is the fact that xj plus 1 equal to f of xj by definition. Therefore, I take this nth iterate and that is equal to fn of x is fn minus 1 of f of x, which is equal to fn minus 2 of f of x and so on. And since I have called the iterate of x naught f of x naught, I called it x1, this cancels this all the way down till you end up with this function here. So all I have done is to write xn minus 1 sorry, this is n minus 2, f of xn minus 2 is the same as xn minus 1 and so on. So I have just inserted these quantities and now you see that this Lyapunov exponent is a property not just of x naught but the entire orbit of x naught, because x naught goes to x1, it goes to x2 and the derivative of this map function at the point x1, x2, x3 are all involved. So it is really a property not just of the initial point but of the orbit on which the initial point lies, and the whole thing will be a function of that initial point. So let me keep this thing here. Can I simplify this? Yes indeed, because it is obvious that at once this could be written as equal to lambda of x naught equal to limit n tends to infinity of 1 over n log of ab is log of a plus log of b. So you could write this as a summation from j equal to 0 to n minus 1 log f prime of xj modulus. F prime of x at every point, the modulus of that is like the stretch factor, the local contraction or expansion factor, and you take suppose take the log of this guy and sum it over the entire orbit and then divide by n, and therefore it is a time average, it is a long time average of the stretch factor. Let us apply to our case. So what is this equal to for our map? F of x equal to 2x modulo 1. So f prime of x equal to 2, no matter where you are the slope is always 2, f prime of x is 2, right, and therefore what does this give you? What is lambda of x naught equal to? It is 1 over n times log 2 summed over n times, and that n cancels out and you end up with a log 2 which is greater than 0. And as I said, every time you have a Lyapunov exponent which is positive, you have chaos, you have chaotic behavior. So you are guaranteed that in this problem you actually lose the error, initial error epsilon amplifies at this rate. You lose 1 bit of information every iteration, iterate. Yeah.
What if x not equal to half?
Pardon me?
At x not equal to half,
Yeah.
do we have any problem?
You see, sets of measure 0 may, for instance, you have, incidentally this is true, not true if you have a periodic orbit, then it is not true. If you start with an x naught which is on a periodic orbit, then it does not expand or anything like that, it is part of a periodic orbit, it comes back to itself. What would be the Lyapunov exponent on a periodic orbit? What would it be? Let's look at the map, let us ask ourselves what would it be. It is a good question. What is the Lyapunov exponent on a periodic orbit? Let us look at the stable periodic orbit. So let me look at this map, f of x equal to ax and a is less than 1, a is a positive number between 0 and 1. What is going to be the Lyapunov exponent in this case? It just becomes a to the power nx, so any initial error epsilon will become a to the n epsilon, and the epsilon divides out, goes away, and then you have log a to the power n 1 over n outside, and so it is log a. And what is log a? Is it positive, negative or 0? It is negative. So you see, if you have a stable fixed point, the Lyapunov exponent becomes negative. Everything falls into that place, everything falls into 0. What about the situation where you have a period 2 cycle? What would the Lyapunov exponent be? If it is stable, if the period 2 cycle is stable, so let us suppose f of a equal to b, f of b equal to a. For stability you would require that the slope be positive, that the slope be the modulus of the slope be less than 1. So this would imply this would be the condition for the stability of a periodic orbit. The slope at each of these points, the product of these two must be less than 1. And what would the Lyapunov exponent end up being? Positive, negative? Definitely negative, definitely negative. So we look at examples. So it could be 0 and it is still not chaotic, but the moment it is positive you have this exponential amplification of errors. Now what I would like to show you is that we have to, by the way, we have computed the Lyapunov exponent very easily in this problem because I knew that the slope was actually constant, so there was really nothing to compute. But if the map is not a simple piecewise linear map, then this is no longer so trivial, and you need a better algorithm to calculate this Lyapunov exponent. And this you can do so numerically, but you actually need some formula for it, which we are going to produce in a while. So that requires a little more information about this map. But before I do that, I would like to point out that this map is random in the following sense. You agree that the rule is completely deterministic. You give me an x0 and I give you a definite x1, it is 2x0 mod 1. So in the forward direction the map is completely unique, it specifies for every x0 I give you a definite x1 and it is deterministic, there is no randomness here at all, and yet it is as random as a coin toss in the following sense, in the following precise sense. Suppose, and this is what happens in real life in a dynamical system, if this is your phase space in a dynamical system, it is very hard to keep track of points to infinite accuracy. You always have some resolution. So what you end up doing is to form histograms. So you partition the phase space into cells. You partition the entire phase space into cells, into little boxes or bins, and on a computer when you do numerics you keep track of how many times the point, representative point, comes into a particular bin. For example, if you are doing it on the unit interval and your accuracy is 1 over 1000, then you would partition it into 1000 bins and you would keep track up to 3 decimal places where the point is and build up histograms, right. Now a representative point could start here and then next time it goes here and then it goes here, it goes here and so on, and you keep track of this whole thing and you build up a histogram over a long period of time, and eventually the histogram which stabilizes will be your invariant measure. It will be the one that is steady state in the steady state. That is what we are trying to discover, and this is called partitioning phase space or coarse graining phase space. Now let us do that with our Bernoulli map, and now I am lazy, I do the simplest possible coarse graining, which is the following. So here is the map, 0 to half and half to 1, this I call one bin and that I call one bin, and this is say the left bin and the right bin. So I am not even interested in whether where this number is, I am just going to keep track of is it less than half or bigger than half, that is it. And as you can see, this corresponds to asking whether each of those AIs is 0 or a 1. If it is less than a half it is 0, if it is more than a half it is a 1. And I do this over a long period of time and I keep track of where the iterates of a random point irrational point r, and I am going to get a long string with L L R R L L R L L R. A typical segment of the iterates of some arbitrary irrational number is going to look like this, a string of this kind. Now the statement of randomness in this deterministic dynamics is that under that Bernoulli shift, it turns out that given any coin toss experiment in which you take a coin and you toss it, and if it's tails you put an L, if it's heads you put an R, you are going to get a long string of L's and R's, and if it's completely random sequence you are going to get all possible sequences. The statement is that for every result of such a coin toss experiment, a string of some arbitrary length formed from a coin toss experiment, there exists an initial condition x0 in the Bernoulli map such that its iterates would be exactly equal to this string. So let me repeat that. Given an arbitrary random sequence, random string with an alphabet consisting of just these two letters L and R, and I look at that string and say, oh, where did this come from? This came from iterating, this came from a coin toss experiment, completely uncorrelated coin toss experiment. It is called a Bernoulli trial, right? You keep doing this and you record this L's and R's. On the other hand, somebody produces for you a string of L's and R's which came by iterating a deterministic rule, the Bernoulli shift. You can't tell the difference. The statement is for every such string which you get by a coin toss experiment, there exists an initial condition x0 which will produce the same string if you did the deterministic evolution by the Bernoulli shift. In that sense, randomness and determinism are very closely linked to each other. This is as random as a coin toss, and this is the marvelous thing about chaotic dynamics, that under suitable conditions the chaos could be so extreme, this is really an extreme form of chaos, that there is no correlation at all. You could ask, what is the correlation? After all, if it is a coin toss, there is no correlation between whether the first 25th toss was a head or tail and the 26th toss was a head or tail, there is no correlation, it is a delta function. That is exactly the correlation even here. All possible strings could occur and it is completely uncorrelated, even though that map is deterministic completely. The job then is to find out what is the density with which it fills things. Already this suggests to you, since L's and R's are appearing with equal frequency, it is suggesting to you that okay, suppose I did a coarse graining like this, 0 to 1/4, 1/4 to half, half to this, what would now happen? The same thing once again. Now you have an alphabet with 4 letters, call them A, B, C, D, and again all possible such sequences would appear and would be indistinguishable from Bernoulli trials. It would be indistinguishable from a suitable die tossing experiment completely. So that is the level of at which this randomness is appearing here. We need to know how to prove that everything is filled up uniformly. So let us do that, and that is interesting because you need to be able to handle things like that. I need to be able to find this quantity, I need a formula for it. In fact, I would be extremely happy if this can be replaced by ergodicity to an integral over the interval, say 0 to 1, that is the interval of the map. Yeah.
So how can the tossing of a coin be random? For example, if we are given the initial conditions,
yeah,
we can mechanistically using Newton's laws tell what it falls. So in what sense it is random?
Very deep question. He is now trying to point out that even the toss of a coin is itself a chaotic machine, because whether it falls as head or tails depends on extremely small changes in the initial conditions. I toss it a little higher, the wind blows a little harder, or the coin is a little oilier, or it lands on its edge and falls this way or that, a little tilt here or there will tell you finally what the distance is. So in that sense, yes, the very paradigm of a random machine, the coin toss or a die, is itself a chaos machine. Yes, that is true. Now we are going to get deeper into this. I am lying a little bit. We do not know how to define a random number. okay. So we will come back to this over and over again. There is really no satisfactory definition of a random number at all. On the other hand, there is no satisfactory definition of what regularity means either. If you give me a piece of music and I ask you, is this random or not, what are you going to tell me? If I play a piece of music up to a certain point, there is no way that you can tell me what the next note is going to be. Of course, if you know what the piece of music is, you know what it is, but if I give you this sample, this little strip, I could argue that this entire piece of music up to this point was a realization of a random process, and now it is going to differ from what the actual original piece of music was in the next instant. But if you give me a finite string, there is no way of telling. So in that sense, everything is random also. So we are going to assume that we have a paradigm of randomness called the Bernoulli trial. How I produce it is a different question altogether. If I produce it with a coin and I am extremely accurate with, I know everything about the coin, then of course I can tell you whether it is going to be heads or tails, and of course you would be able to, you must have enormous computing power to be able to do this. That is the whole point. You have to tell me with arbitrarily high precision how I toss the coin, then I can predict. Have you read this book called the Newtonian Casino? How many people have read this? Well, in the early days of chaos, a bunch of people in the US tried to break the Las Vegas casino system, which is of course run by the mob, so it is dangerous to try to do this, by smuggling, by sort of in the early days they had wired themselves, and they had a computer program which would actually calculate where the roulette wheel is going to stop, and they tried to break the casino by doing this, by putting in the initial conditions and solving these equations numerically to see where it is going to end and so on. It is now illegal to do this because it is very dangerous, and illegal to do this because it is possible to some extent to make predictions, but to the extent that these machines are more and more sophisticated chaotic devices, it is harder and harder to do this. In principle you need infinite precision to do this, right. Okay, well, that is a good conceptual thing. So I would like to be able to write this guy as equal to an integral dx some density times log mod f prime of x. I would like to be able to do this. I would like to be able to find this rho of x. If I can do that, then the job is done. I can calculate the Lyapunov exponent in this problem in terms of this invariant density rho of x. And the question is, how do I write an equation for rho of x? And this is going to take us to this very basic question of where does dynamics stop and where does statistics begin, where does statistical mechanics begin, because we are really getting into that right now. Unlike statistical mechanics, which leads to thermodynamics and so on, as we will see a little later, there is no extra input here. The rule of the game is the dynamical equation itself. I give you a map function and that is the end of it. Everything has to be produced from that. How do I do that? Well, I argue as follows. Suppose I start with a point x0, then under the map this goes to an x1 equal to f of x0. Okay. Therefore I can ask, what is the probability density of the point x1 after one iteration? You give me x0, I give you x1, but now I ask what is the probability density of x1. Of course, since there is a definite sharp x1, the answer is that it is a Dirac delta function. At which point? In terms of x0, f of x0. So the probability density at the end of one time step of reaching a point x1 is equal to delta of x1 minus f of x0. Do you agree? I could have reached any x1, but I reach only that x1 which corresponded to f of x0 because I give you x0. What is rho of x2? I put this here to show that it is after n 2 time steps. What is this equal to? This is equal to a delta of x2 minus f of x1, of course, provided x1 is given, but if x1 itself is uncertain and it was x0 that was given, so this is equal to delta of x2 minus f2 x naught. You could also write it as delta of x2 minus, you could also write this as delta of x2 minus f of x1 delta of x1 minus f of x naught. Would this be correct? Should I write it like this? Is this correct? I have to integrate. I have to integrate over what? Over some interval. Over what variable? x1, because it says starting with an x naught I go to an x2 through an intermediate point x1 and I have to integrate over all possible x1s, but the system, this delta function will pick out that x1 which is equal to f of x naught. So I have to integrate over the intermediate guy. So I could write it like this or like that or like this. Everything will depend on x naught where I end up, and I am asking for a density in x2. So there shouldn't be any x1 in there, it just gets integrated over. So now what is the moral of the story? If you give me a point y, under the iteration it goes to f of y. Therefore if I ask after n time steps what is the probability density in x, this is equal to an integral over all y's delta function of x minus f of y multiplied by rho n minus 1 of y. So he says I start with some initial density, x naught itself is arbitrarily defined with some density, it goes to a whole spread of points x1, every x naught goes to f of x naught, a spread of x naughts goes to a spread of x1s by this rule, and it says you give me the density at the n minus 1 time step, if that is rho n minus 1 of y, each of those y's goes to a particular x by this singular kernel here, and if I integrate over all y's I end up with the density at the nth time step in x. Right? That is my dynamical equation. It is now an evolution equation for probability densities, not for the variables themselves. So we have gone over to a statistical picture already. Okay. Is this equation clear? It is equivalent to saying rho 1 of x1 is delta of x1 minus f of x naught, provided I have a sharp x naught, but if I have a density in x naught, rho naught of x naught, then I must integrate over all possible x naughts with that weight factor to produce the density in x1, and similarly for 2 from 1 and 3 from 2 and so on. So this is what the equation is. That is the evolution equation for the density. Yeah, we do not know rho naught. You give me any rho naught, I tell you what rho n is by this prescription. So what has happened is the dynamics now has gone into statistics in some sense by saying if you do not know your initial condition but you know what its probability distribution is, I will tell you the probability distribution of the nth iterate. Now what happens if you take the limit n goes to infinity here? Well, rho n minus 1 is not distinguishable from rho n when n goes to infinity, whether it is n minus 1 or not does not matter, right. So it is clear that if you take the limit n goes to infinity here, then if there is a limit, if this function has a limit, that limit would satisfy rho of x equal to integral dy delta of x minus f of y rho of y. This rho and that rho are the same. If the limit exists, it is in this sense that the Maxwellian distribution of velocities in this room is an invariant density. Okay. Each of these particles is colliding, but if they are distributed according to the Maxwellian distribution, even after the collision it is still a Maxwellian distribution. So even after the dynamics has taken place, which is buried here, you still have the same distribution. That is the meaning of equilibrium. And since this distribution does not change under iteration, it is called the invariant measure. This is called the invariant density. What sort of equation is this? Is it a differential equation for this rho of y? Is it an integral equation? Yeah, it is an integral equation. It is not a differential equation, it is an integral equation. It says you have to find rho of y, this is an unknown quantity. You are given f of y, you are given this kernel, and this is an example of an integral equation which looks like this. If you have a phi of x given by some integral dy, a kernel k of xy phi of y, this is called an integral equation, an example of an integral equation, and this quantity k, this is a function of x and y, is called the kernel of the integral operator. Is this a homogeneous equation or inhomogeneous equation? Homogeneous. If you multiply rho of y by a constant, it cancels out on both sides. So it is certainly a homogeneous equation. Is it an eigenvalue equation? Do you think it is an eigenvalue equation? Yes. This is some operator acting on phi of y and it produces the same phi. What is the eigenvalue? 1. So it is actually an integral equation, a homogeneous integral equation with eigenvalue 1 of this kernel k of x comma y. Is this of that type? Is this equation of that type? Yes, indeed it is. But is there something special about the kernel? It is a bad kernel, it is a delta function, it is a singular kernel. So you see you have this equation, but it is a singular integral equation. The kernel is singular, this equation has a name, it is called the Frobenius Perron equation, and it is a singular integral equation. So the matter is not so trivial, you still have to deal with some mathematical complexities and you have to solve this equation, and of course if the x variable is in many dimensions, then you have to solve a multidimensional equation. It is not a trivial problem at all, but it is a homogeneous integral equation and you would like to find that eigenfunction which has eigenvalue plus 1. Is there any other requirement on rho? How are we going to find this? Because after all I can multiply this rho by a constant and I do not change anything. I normalize, I need to normalize, of course. What is the normalization condition on this rho? Over the interval I, this could be the unit interval or whatever interval you are, 0 to infinity, minus infinity to infinity, we do not care, whatever is the range of this map, over that interval if you integrate this invariant density you should get 1, that is the normalization condition. So is there any other requirement? Yeah, it can't be negative. Rho of x is a probability density, so it can't be negative. It could be 0 at some points, we do not care. Can it be infinite? Yes, why not, why not, but it has to be an integrable infinity. You still must satisfy that condition, the total area under the curve must be 1, the function may be unbounded, so you still have to put the condition rho of x greater than or equal to 0 for all x in this interval. Could be unbounded, could well be unbounded. You are familiar with unbounded densities, there is no reason why you take a pendulum clock and it is swinging back and forth in this fashion, and I ask what is the measure invariant density of the angle, of the angular amplitude, what would you say? I go to a clock shop in the old variety, not the modern day clock shops, and I take a photograph of all the clocks they have on display. Let us assume the old fellows got on display a whole lot of pendulum clocks. You invariably notice that most of the pendulums are either like this or like that, very few of them are like this. Why is that? Yeah, because out here the velocity is 0, it is about to turn, it is about to turn here, it spends more time there than it does here, it zips through here and then it does that. So you take a random snapshot, most of them are going to be like this or like that. So it is immediately clear that if you are going to take snapshots at random intervals of time uniformly over a time period, then the angular distribution is no longer going to be uniform, it is going to be predominantly like this or like that. That is easy to find out, because if the solution is something like theta of t equal to theta naught cos omega t, if that is what the oscillator looks like for simple harmonic motion for example, this would imply that omega t equal to theta of t, let me just call it theta, theta over theta naught implies t equal to 1 over omega cos inverse theta over theta naught. And then of course you know that if the probability density in theta is p of theta and the probability density in time is just uniform, then you know that p of t dt must be equal to p of theta d theta. If at time between time t and t plus dt the angular amplitude is between theta and d theta, the probabilities must be conserved on both sides. So this is certainly true, we need to have these guys positive, so you must have that sitting there, and therefore this implies that p of theta equal to p of t modulus dt over d theta, modulus. But p of t is equal to 1 over capital T, the time period, it is uniform in a time period and keeps repeating, so just some constant. And then dt over d theta is not hard to find, because you know that d theta over dt equal to theta naught omega sine omega t, and I take the modulus of this guy, and therefore there is no plus sign, this thing there, and I invert it and I write it in terms of theta. So what does this give you? D theta over dt is just sine, so what does that give you? dt over d theta gives you a sine in the denominator, but I must write it as a function of theta. So what does it give you? Goes like this, some constant, we do not care, we will normalize it, 1 over square root theta naught squared minus theta squared. So the probability distribution in the angle is not uniform, it is in fact predominantly towards theta equal to theta naught, because it becomes infinite at those points. What does this graph look like? It is infinite at those points, does that, this symmetric function, it blows up at the two end points, it is actually infinite, but the area under the curve is guaranteed to be unity. So probability densities can become infinite, become unbounded, we do not care, but it is a square root, inverse square root singularity and can be integrated, gives you 1. And now you see of course immediately that this is the probability that you are in a small range d theta near the left end of the amplitude, and similarly for the right end, and of course that is much bigger than this. So that is why you do not see it ever in the middle, but you see it here predominantly. So remember, if you have two variables related to each other and one of them is got a uniform distribution, there is no guarantee the other one has a uniform distribution at all, you could have a bias, and that is exactly what happens. So all you need is that this guy be positive, nothing more. Now let us apply this immediately to our problem of the Bernoulli shift. We can write this down, so this is equal to for the Bernoulli shift this is equal to integral 0 to 1 dy a delta function of x minus f of y, but what is f of y? It is 2y modulo 1, right, but that, so that is not going to be so trivial because f of y equal to 2y modulo 1, that is equal to 2y for 0 less than y less than half, and it is equal to 2y minus 1 for half less than y less than equal to 1. So you got two different functions altogether, and you have to use that fact here, and therefore I have no choice but to write this as 0 to half delta of x minus 2y rho of y plus integral half to 1 dy delta of x minus 2y plus 1 rho of y. No choice but to do this. But can I do this integral using the delta function? Yes, I can, but I have to use the fact that I must write it as a delta function of y minus something, only then can I do it. So I need a formula which says what should I do if I got a delta function in a function of y. I have to convert it to a function of to y minus whatever, and what formula would you use? You need to use the fact that delta of ax is 1 over modulus a delta of x, and it is a symmetric function. So I could write this as delta of y minus x over 2, but I have to pull out the 2 and write it in the denominator, and it is equal to this, and I have to do the same thing here. So this is equal to y minus x plus 1 over 2 rho of y and a half. And then the next step is I can do this integral provided the delta functions fire. But you see, if I go back to the map function, this was the first branch, the left branch, and this is the right branch, and it is this function that I have written here, and it is this function that I have written here in this place. And the idea is that for every x between 0 and 1, any x I put, there is a certain y, the delta function contributes as y runs from 0 to 1. Therefore I can straight away do this integral and write this as equal to 1/2 rho of x over 2. Wherever y appears is write x over 2. Similarly, for every y between 0 and 1, half and 1, there exists an x, the map function fires, and so I am guaranteed that I can use the delta function and write it as rho of x plus 1 over 2. That is my Frobenius-Perron equation. Rho of x is equal to this thing here. Is this an integral equation? No, there is no integral. Is it a differential equation? No, it is a functional equation. It says rho at any argument x is the average, is the arithmetic mean of rho at half that argument plus 1 plus that argument over 2. It is not easy to solve. There are no algorithms to solve functional equations at all. But now you have to take it from me as an article of faith that this is an intricate problem, that if you have a Frobenius-Perron equation of this kind, this has now become a functional equation, and you have imposed the condition of non-negativity and the fact that it is integrable, normalizable, then there are theorems which tell you under suitable conditions which apply here that a solution, if it exists, is unique. You are armed with that, and therefore once you know a solution, if it exists, is unique, you can make guesses. What would be the simplest guess? It is a constant, and this thing has to be normalized to unity between 0 and 1. So what should the constant be? 1. Yeah, 1. Suppose I put rho of x equal to 1, what happens? It obeys it, and therefore guaranteed that is the solution. and moreover it is a unique solution. This is not always going to happen, but in this case it happens. So but you need that very powerful theorem which is not easy to establish, and then it turns out that the solution is in fact a constant density. This is why I asserted that the iterates of irrational points on the Bernoulli shift would uniformly and densely fill up the unit interval. Of course with the infinite number of exceptions, all the rational points, but they are a set of measure 0, but they are dense. You need them, you need those unstable orbits to spew these trajectories on either side of each of these unstable orbits and produce this chaos, but having done that the job of those points is over. The rest of the points would uniformly and densely fill up this entire unit interval. The unit interval is called the attractor now, the whole interval has become the attractor completely. Not always true, but in this particular problem it turns out to be true. So indeed we can now that we know this, we can compute the Lyapunov exponent. Lambda is equal to of any x naught which is irrational is 0 to 1 dx rho of x, which is 1 times log mod f prime of x, but that is log 2, therefore it is equal to log 2. So we do not have to go through this long time series, we can apply a formula using this rho of x and that is it. What is the value of log 2? Point whatever it is, 0.693 log 2, 0.693, okay, so it is positive, that is what you need. Suppose I had not done the Bernoulli shift, but I had done f of x equal to 3x modulo 1, what would happen? You would have log 3 as a Lyapunov exponent. Again all points which are rational would be parts of periodic orbits. If you write it as ternary decimals in an alphabet containing 0, 1 and 2, then all decimal points which would all numbers whose decimal expansions would either terminate or recur would lie on periodic orbits, and all irrational points which are really a set of measure 1 would become chaotic, completely chaotic. So these Bernoulli shifts are very, very simple examples. As you can see, they already have a fairly complicated amount of mathematics in them, because if you ask what are all the possible eigenvalues of this operator, so you can put a lambda here, do not call it rho of x, call it phi of x, then it is very intricate, completely it is very intricate. If you relax those conditions of positivity, non-negativity and normalizability, then the thing can get extremely complicated. You may not even have continuous functions, you may have fractal functions and so on. So the full set of eigenvalues is highly non-trivial, but we are looking for a very, very simple eigenfunction which is unit eigenvalue, the largest eigenvalue, and it is non-negative normalizable. The answer is it is just a constant, it is easy in this case. Now what I will do tomorrow morning is to show you that this map is actually dissipative, but we would like to mimic Hamiltonian dynamics, which is conservative, measure preserving. So we will change this a little bit and I give you a similar kind of shift, a slightly more complicated 2-dimensional shift, which would in fact be measure preserving. So we will look at that, and then this will lead us in another couple of lectures to statistical physics. Okay.